Hello once again, class. Let us continue our lecture on the topic work and energy. So this time I'm going to show you the third example where we can apply the work and energy method to solve this sample problem. Alright, so this is our third example. A spring is used to stop a 30 kilogram package which is sliding on a horizontal surface. The spring has a constant K equal to 20 kilonewton per meter and is held by cables so that it is initially compressed 120 millimeter. The package has a velocity of 2.5 meter per second in the position shown. Okay, so this is a illustration. And maximum deflection of the spring is 40 millimeter. So determine A, the coefficient of kinetic friction between the package and the surface, and B, the velocity of the package as it passes again through the position shown. Alright, so here's the solution of this problem. Once again, we have to apply the principle of work and energy between the initial position and the point at which the spring is fully compressed and the velocity is 0. So the only unknown is the relation in the relation. The only unknown in the relation is the friction coefficient. Okay? Then apply the principle of work and energy for the rebound of the package. So the only unknown in the relation is the velocity at the final position. Alright, so here's the illustration. We have here a package of a mass of 60 kilograms with a velocity of 2.5 meter per second going into this direction to the right. The spring here is held by this cable. Okay, so there is the span between this package and the spring is 600 millimeters. Okay, so applying the principle, we have principle of work and energy. So we have initially V1. So this is given the problem. So this is the initial position 1 to 2. So initial position of the package and the second position of the package is this one. So initially the package is here, position 1, and then after it travels or moves to the right, so this is now the second position. So initially we have V1, the velocity of the package. Right, then when it reaches to this destination, it will be stopped by the spring. So the velocity here is equal to 0. Okay, so the span here is 600 millimeters, and this the the distance. Okay, so the due to the impact, no. So we have here this is 40 millimeter, the deflection. Okay, so solving for the kinetic energy at this position 1, so we have T1 here, that is 1 half mv sub 1 squared equal to 1 half. The mass here is 60 kilograms, that is the mass of the package, multiplied by its velocity and then squared. So we got here 187.5 joules. Okay, so that's the unit of the um, kinetic energy. And for T2, T2 is equal to 0 because the velocity here is equal to 0. So again, T2 here is 1 half mv sub 2 squared. So since V2 is equal to 0, so naturally T2 becomes 0 also. Alright, now resolving this illustration here into these forces. So we have the weight of the package, and there's a force normal to that on the surface, and we have the friction, no friction that will oppose the direction or the movement of the package to the right. So of course it should be going to the left. So we have this relation that the force, this force F here going to the left, that is the frictional force, will be the product of the coefficient of friction and normal force, this normal force. Okay, so Um, Using this illustration here, solving for the work, no work of the package due to the package moving towards the right. So we have u sub 1 to 2. So this represent the work equal to the, this is equivalent to mu sub key, mu sub key times w then times x, right? So we have 600, 600 plus 40, so meaning the total here, the total is equal to 640 millimeter. So this would be 640, 6. Okay, this is just the sum of these two lengths here. Okay, so work, so that would be multiplied by its displacement, because this is considered as the force. No, when you multiply the coefficient of friction with its weight, so that would be the force, then multiplied by its displacement x. And the total displacement is equal to 640 millimeter, or simply 0.640 meters. So when you multiply this one, so we get the force, the work from this position to this position. Okay, work done by this force due to the force applied to this, or the velocity of this package going to the right. Okay, so this is equivalent to negative 377 joules multiplied by the coefficient of friction. Okay, so remember this one, we will be using this equation in our next equation to solve for mu sub k. So apply the principles of work and energy. So again, we have here V sub 1, V sub 2 is equal to 0. We have here the P minimum, so the force needed to make this package move. So we have the minimum force that is equal to the product of the constant, no, coefficient of the constant multiplied by x sub 0. This is the mentioned problem. There's an initial displacement of 120 meters. So multiplying this, so k, this is a given in the problem, that is a constant, multiplied by x sub 0. So this is the initial, because there will be initial compression here, because due to the pull of the cable. All right, so we get here the minimum is 2,400 Newton. Then the maximum, so the maximum would be the product of K and X sub 0 plus this delta X, the displacement when this is displaced. Okay, so as mentioned in the problem, so we have here the displacement equal to 0.160 meters. Okay, so we got here 3,200 Newton. So that is the maximum. Now the work done, so the work due to this force, this minimum maximum force, so we have 1, 2. This is when it involves spring, we have this formula that this is equivalent to 1/2 times the minimum force plus the maximum force multiplied by the displacement. Okay, so substituting the resulting values, we have 1/2, negative 1/2 times 2,400. This is the minimum, plus 3,200 Newton. This is the maximum. Then the displacement, that is 0.40, no, zero point 0, this one. Okay, so after it hits, there will be a displacement. So multiply by this, because again, work is equal to the product, no? The product of the displacement, the product of the force and the corresponding displacement. So we have L, or you can say S is the displacement. Okay, so substituting, so we got here 11 or negative 112 joules. Now to find the work, no? This is the sum of these two work. So this one, when we solve for T1 from here, okay, so we got this value, U, or work from 1 to 2 subscript F. This is the product of coefficient of friction and the weight multiplied by X. So we get this, right? Then this one, work 1 to 2, this is 1 half, considering the spring, minus 1 half times the sum of the minimum force and the maximum force multiplied by delta X, the displacement. So in this case, we have 1 half, this is the maximum force, this is the, this is the minimum, and this is the maximum, then multiplied by delta X. Delta X is this, the displacement here. So which give us negative 112 joules. Okay, so from this work from 1 to 2 is just the sum of the two works. 1 to 2, that's the one shown in the previous slides, and plus this one. Alright, so combining these two, so we got uh, minus 377 joules per multiplied by coefficient of friction equal to minus 112 joules. Alright, now we have this equation, T1 plus U, or the work from 1 to 2 equals to T2. So this one, T1 is calculated. So substitute this, and then work from 1 to 2. So this one. So we get this as 377 multiplied by mu k minus 112 joules. Okay, so combining. So when you combine these two, 187.5 joules minus 1112 joules, then transpose the other side. So the difference, so you combine this one with this, okay, and this is negative, so try to transpose this part. This is a negative product of 377 joules multiplied by mu sub k, so transposing this to other side, so this becomes positive, and then you have here the combination of this one, so you have positive because 187.5 minus 112, so you have something 100 plus. You divide both sides by the coefficient of mu sub k, so you get mu sub k equal to 0.25. So this is the resulting coefficient of friction. All right. So next, we will solve the velocity. Okay. Right. So solving for the velocity. So now another scenario is that when the package hit the spring, it will bounce. No? It will bounce. So we have here at this position, the velocity is equal to 0, but when it bounces, so there will be another velocity here. So we have here this point 2, and then this point 3. Position 2, then position 3. So again, this is the total distance, 640 meters. Okay, so from this illustration, we have T2. We know that at this position of the package, so T2 here is equal to 0 because the velocity here is equal to 0. Now T3 would be 1 half m, 1 half times m times v sub 3 squared, which is equal to 1 half times 60, because the weight of this package is 60, times v sub 3 squared. Okay, so let us resolve uh, forces here. Let us have an equivalent representation of this illustration here in our free body diagram. Okay, so the when the package hit the spring, it will bounce. Okay, so it will bounce. So again, there's a coefficient of friction here. There's a frictional force that will oppose that bouncing of the package. So we have here F to mu k times n. So that is the direction. The force here that will push is the one caused by the spring. Okay, so we have the work from this position to that position, from 2 to 3, equal to u, meaning work from 2 to 3, the F plus the one that is in E in our previous calculation, which is equivalent to, this one is already done, this was calculated, plus this is also calculated. So we get here the work from this position to that position, from position 2 and to position 3, so equal to positive 36.5 joules. Alright, so from the standard equation, we have T2 plus U uh, work from 2 to 3 equal to T3. So T2 again is equal to 0. Oh, the T2 is equal to 0, as you can see here, because velocity at this point is equal to 0. Okay, so we have only this one, and we have calculated this. So this is already given. Okay, which is equal to this one, right? So substituting equal to, so substitute T3 is 1 half 60 times V sub 3 squared. So from here we can solve for V sub 3, that is equal to 1.103 meter per second. Okay, so this is the solution to this third problem. Alright, so I think I will stop up to this part. So you have already 3 examples, and I hope you will practice this exercises class. Okay, so we have few numbers here for your exercises. You just use the same concept class, and there is an additional example here. Okay, but for the rest, try to practice class for some exercises. Okay, so that's it. Thank you very much, and hope to see you again in the next video. Bye.